In this video, we're going to learn about the squeeze theorem. So squeeze theorem is when you're given three functions and then you're trying to look at the limit at the same point of those functions. So I'm going to kind of highlight some of this. So trace this to be purple, if you can tell that that's actually purple. So we have a function on top of it and a function below it. If you notice, the function on top is always larger than the function in the middle, which is larger than the function in the bottom. Okay, at least for what we need right now in this little spot. So all it's saying is that if h has the same limit value at this point A and f has the same limit value at that point A, then it stands to reason that g has the same limit value at that same point A, and they're just calling the height L just to generalize it. Okay, so that's all the squeeze theorem is, and it does need to fit these prerequisites that the function has to be between the other two functions. In that it just needs to be in some interval that does contain A. All right. So now let's see what some problems actually look like. So this top example right here, it's saying for all x in between -1 to 1 that this is a true statement. It wants us to find this limit right here. So the first thing I'm going to do here is I'm going to use the squeeze theorem because this is already set up nicely for me. So I'm going to, by the squeeze theorem, I'm going to look at the limit as x approaches 0, again because I'm looking at 0, of the square root of x to the 8th plus 7. In this I can just directly plug in and get root 7. If I do the same thing on this side over here, for the value that's larger, plug in a 0, I'm also going to get a root 7. So it stands to reason by the squeeze theorem that the limit x approaches 0 of h of x is root 7. That did not answer my question because I'm looking for this right here. So now I'm going to use my limit laws and split this up. So the limit is x approaches 0 of h of x plus the limit as x approaches 0 of 25. Well, this is root 7. And this right here, there's no x to plug in because it's a constant. You're just going to get that 25, and that is your answer. And then the one below it is we're going to use the squeeze theorem to evaluate this limit right here. So it's kind of a bummer for this one is it's not set up for us, so we're going to have to set it up. So we're going to set up the squeeze. So usually with these squeeze theorem problems, we're looking at the trig values. Okay, so I'm just looking at the range for sine. The range for sine is that sine is between sine of anything, mind you. That's why I can do 1 over x is always between -1 and 1. Okay. So for all of these, using the squeeze theorem, we always just we look at the trig or something weird that's going on. We wouldn't use the x quite yet. We always start with the more complicated function. So in this case, it's going to be the sine. And then now, if I multiply everything through by x, I'm going to get -x, x sine of 1 over x, and then x. So now I can use the squeeze of -x is equal to 0, and the limit as x approaches 0 of x is also 0. So then by that squeeze theorem, we're going to get that the limit as x approaches 0 of x sine of 1 over x is indeed 0. Now you did need to use a squeeze theorem for this one, because if we're looking at this function again right here, I can't just plug in a 0, because I would get 0 times sine of 1 over 0. So, and you can't have something be over 0 like that, especially inside a trig function, because usually for this you would get like an infinity or negative infinity or whatever if you have a number over 0, but this is inside of a trig function, which is cyclical, because it goes up and down and up and down and up and down, so that wouldn't help us. That's why we needed the squeeze theorem for this problem, and that concludes the squeeze theorem.